Hi, this is Alan Sguigna of White Knight Labs. Today I'm going to do a demonstration of Microsoft's WinDbg time travel debugging functionality, a very powerful and underutilized capability within the Windows debugger that gives us the ability to travel both forwards and backwards in time to triage root cause and to do malware research and threat analysis. So let's have a look at how that works in real life. So what we have here right now is a little application I've created that will cause an exception in user space. It starts off by doing a print on hello world, then sets up an integer, a couple of variables, a pointer. It sets the pointer to be a null, and then it does the dereference of that pointer, and therefore causing an exception. So let's just see what that looks like just by doing a run from within Visual Studio, and the hello world comes out, and then the exception is thrown. And you can see over here the NT status associated with an access violation. So that's going to happen. Very simple program, but we'll highlight the use of the WinDbg TTD functionality. So let's go over to WinDbg and fire up time travel debugging and have a look at what's happening here within this program. So under the File menu, we mosey over to Launch Executable Advanced. Make sure that your executable path is pointing to, in this case, null pointer read, the little program that I wrote. And we want to check that box to set up time travel debugging, do a configure and record, and then do record. And what it's going to do, it actually runs the program twice. It runs the program. If you look at the command window output, you'll have seen that the exception is thrown. What TTD is doing is setting up an emulated environment for the program to run in. So that slows it down. TTD typically runs any program 5 times up to 20 times slower than its normal speed. But you do, in fact, capture state instruction by instruction, so which is unlike any other debugger, at least in the Windows space and the x86 space. So extremely powerful. All right, so what we've done is we land at the typical instruction pointer, within any initial break, within WinDbg. Let's have a look at our source code here. Let's bring our source code into the picture by doing the open a source file. And there's my null pointer read C++ program. And then let's do an enter there. Let's close up this here, the timeline here. And now you can see the source code on this side, the disassembly with symbols over here, registers, locals, none yet, and then the stack itself. All right, so what we want to do now is to go into our program. So there's a few different ways of doing this. I've got symbols set up, so I'm going to put a breakpoint at the entry point to my little program. Sorry, let's put an exclamation mark there. And you can see the breakpoint shows up in the source window over here at the entry point. And we'll just simply do a go, right, to hit that breakpoint. And then we'll step through the program itself and watch what's happening, both forwards in time and backwards. You'll see with TTD, we're in that emulated environment. So we've got a new section in the ribbon here at the top, reverse flow control. So you can see let's look at our instruction pointer here in the disassembly window. You could do a step into, of course, right, as you would with any other debugger, and that moves the instruction pointer down a couple of instructions, or you can do a step into back over here, and a couple of those put you back to the entry point. And the register windows change accordingly, the stack and so on and so forth, right? Everything is reflective of going forwards and backwards in time. So let's hit a go, and we'll hit my breakpoint here. So you see in the source code window, the instruction pointer shows up there. And now we're at null pointer read, the entry point, the main entry point where the push RBP happens. All right, so let's watch what happens now with a simple go, right? Because WinDbg is set up to do a first catch exception, right? If we hit go, we know we're gonna do that null pointer dereference, right? And crash. So let's do that and hit go. And as expected, the instruction pointer moves down to the offending source level instruction and assembly level instruction here. And it's this instruction, right? Once executed, we can see RAX, which is being referenced in place back in RAX, is at 0. So that causes our problem here. Now, hypothetically, we could go backwards in time. The real offending instruction that erroneously set RAX to 0 could be hundreds or even thousands of instructions backwards. But we can go back just even one instruction or two instructions and see, okay, at this instruction here, after it's executed, we see looks like a valid address here, pointing somewhere probably in this general area of the program itself. But then the step into is setting it to 0, right? And which once executed, causes the crash. So you can see this is a simple program, simple demonstration. You can see that it's with the offending code very, very close. It's pretty simple to see. But if you were triaging a very difficult and challenging issue, or looking at a very sophisticated bit of malware, this could be a tremendously powerful and useful tool to give insight into root cause. And I hope that helps.